All right, so for this problem, we start with $2,000. We're earning 10% per year. We want to know how much it's worth in 15 years if the interest is compounded first annually. Annually is the nice simple equation. That's the one where we can just do p times 1 plus r to the t. If you're thinking back to that equation we just learned with n in there, that'd be fine, but n would be 1 here because we're only compounding once per year. So we can do that calculation. We get $8,354.50. Great. All right, what about monthly though? Well, for this one we do have to go back to that new equation with n in it. And this is what we end up getting when we actually do that work. Now, if you didn't get that, let's see where we got that from. First of all, there's 1.0083 with the 3 repeating. That comes from doing 1 plus r over n. Now, r in this problem is 10%, which turns into 0.1. N, remember that's the number of times it compounds per year. If we're compounding monthly, that means 12 times per year. So that's where that number comes from. I'm actually calculating 0.1 divided by 12 and then adding 1 to it. And then the 180, well, that's n times t. And n, again, was 12, and t was 15. 12 times 15 gives us 180. So that's where that's coming from. And then finally, we're going to repeat the process for daily. And it really is, again, the same exact equation. The only difference is that it's no longer going to be 12 in our equation. For daily, there's 365 days in the year, so we do 365 instead. When you do that, you should be getting an answer of about $8,961.54. Now, one thing I want you to note here about those 3 different numbers we just found. Notice that when we compounded more often, the amount that we had at the end increased. And so then that brings us to that last question. What about the idea of continuously compounding interest? So the idea here is that annually means we compounded it once per year. Monthly was 12 times per year. Daily, 365 times a year. We could go hourly. We could go every minute. We could compound every second. And as we do that, as we cut it up into smaller and smaller time pieces, that end value is getting bigger. The idea of continuously compounding interest is the idea that the end value is approaching infinity. In other words, it's getting so insanely huge that it's basically happening all the time, that we're compounding on the last value. So the question then is, what happens in that sort of a situation? And that's going to be what we're dealing with today that's going to be new. Now, the first thing that we have to deal with is that if those end values are getting absolutely huge, does that mean that our final answer is just going to get huge and we're going to be able to get like an infinite amount of money?
Yes.
If only, right? There's actually a limit to it. And if you wanted to find that sort of limit and figure out what was pretty close to it, you could actually try an end value in our equation that we learned yesterday and try putting in some absolutely ungodly huge number in there. Or we can actually use a formula that's actually dedicated for this very purpose. Because this idea where it's approaching this certain value, it actually has a certain number that can be used to represent it. And then the formula changes based on that. So we're going to add this into your notes. This is a new version, and actually even not necessarily a new version of the old equation. It's a new equation, because you notice the r and the t are now in the exponent. All right, now you'll notice something new in this equation, that e. The easiest way to think about e is that it's like pi. Pi is this number that came up so often, and because it was this irrational number, that is, it's a decimal that never ends or repeats itself, and it came up so often that they just gave it a name. You know, they said, rather than trying to say, hey, remember that 3.14 number? They said, it's pi. E does the same thing. E comes up in a lot of different applications. And so because it comes up so often, they gave it its own name. They chose to call it E. And so from now on, when you see E in an equation, don't be thinking that it represents some unknown. E actually is going to be like pi. It represents an actual number. And you can see what that number is down here. It's about 2.718 and so on. Now, I want to make sure you can get that number out of your calculator here too, because we're going to be doing some calculations on E. Now, when you look at your calculator, it tends to appear not necessarily as E, but instead as e to the power of x. You tend to have an e to the x button rather than just an e button. And so knowing that, find that button, and then I'd like you to please calculate the value of e to the power of 1, because that should just equal e, so you can make sure it's giving you that same value, that 2.718. If you're on a scientific calculator, you'll type in 1, and then press the e to the power of x button. If you're on a graphing calculator, you'll press the e to the power of x button, and then tell it that you want it to be to the power of 1. All right, so we put this equation together a little bit differently when it comes to continuously compounding interest, and that's how we know to use this equation when you see that word continuously. If it says monthly or annually or something like that, you're still using the old ones that we learned before. So now going back to the problem that we were just doing, we're looking to see what if the interest in this situation is compounded continuously. So I'm going to plug the numbers into this new equation that I got. So our equation is p times e to the rt. P is principal. That's our starting value, same as it always has been. So it's still 2,000. Then it's times e. Well, remember, e is just e to the power of rt. R is still our percent turned into a decimal. So for my R value, I still want to do the 10 divided by 100. So that's why it's 0.1. And then it's RT, so I'm multiplying that by our T value here, which is 15 years. So it's 0.1 times 15. Now the easiest thing to do when doing that calculation is to do the 0.1 times 15 first. So that gives me the 1.5. Once you know that, go ahead and do e to the power of 1.5. Get that number and multiply it by 2,000. You should be getting an answer here of about $8,963.38. Make sure you can get that before we go forward. All right, so now once we've seen how to do that, now we can go ahead and apply it to a new situation. So here's the problem that we're going to be working with next. Write down the highlights as we go. So a house is currently valued at $200,000. Start at $200,000. There's a highlight to make note of. If its value is increasing at an annual growth rate of 3%, so we're growing by 3%, there's a critical piece of information. Compounded continuously, definitely want to make note of that, because that tells us which equation we're going to be using. How much will it be worth in 25 years? So there's really 4 critical pieces of information that we have going on here. Now, of those, the compounded continuously is the one that tells us which equation to use. The rest are all aspects about what we plug into that equation. So I can go ahead and start writing my equation. So when writing it, first up we have a of t. Do I know what my final value is supposed to be in this problem? No. In fact, that's what we're looking for, right? Because it's saying how much will it be worth. So it's going to be a of t. Now what is t here? 25. Yeah, we were told it's going to be after 25 years. So a of 25 equals p. Okay, p. That's just like what it's been before. Principal. That's going to be 200,000. Then that is going to be times e to the rt. Remember, e, it's a number. When you write e, you're just putting in a placeholder for that big long decimal. So it's not like I've introduced a variable here. That's just some number to the power of rt. Now r comes from 3% here. So I'm going to take my 3%, divide it by 100, and that's going to give me 0.03 for my r value. And that's going to be times t, and remember I already know that my t value is going to be 25. And so I have my equation. Now you have something you can calculate. When doing the calculation, I definitely suggest do the 0.03 times 25 first, and then you can do e to the power of that, multiply it by 200,000, and see what we get. If all goes well, you should be finding that a of 25 equals $423,400. And yes, that actually is accurate out to the hundredths place. This one just happened to round to a nice, pretty number. All right, so having seen that, that's where it's fairly typical where we plug in for t. We're used to that type. But we've also been doing problems that look like this. Now this problem, very similar, except that what it's asking for is different. I'm still starting with 200,000. The value is still increasing at a growth rate of 3%, and it is still compounding continuously. The difference is that here we're being asked, how many years will it take for it to be worth $600,000? All right, so let's write the equation for it. So the first thing I put into my equation is the A of t value, my final value. In this problem, I actually know what I want my final value to be. I want that to be the 600,000. So it's going to be 600,000 equals. Now this is still compounding continuously, so it's going to be 200,000 times e to the RT. E is still 0.03, and t is my unknown in this case. So now I have this equation that I'm going to try to solve. All right, now as usual, if I'm trying to solve an exponential, the first thing I want to do is get the exponential part by itself. So that means I got to get rid of the 200,000. And since it's being multiplied by it right now, I want to divide both sides by 200,000. Isn't that nice? It works out to be a nice, pretty number. It's just 3. Almost like it was planned that way. All right. Now we need to solve this. We're solving for an exponent. Whenever we solve for an exponent, we do so by then writing it as a logarithm. So I'm now going to rearrange this exponential into logarithmic form. And when we do that, we get that it's 0.03t equals log base e of 3. This is where things could be a little bit smoother, and we're going to be talking about how to smooth them out a little bit. Because trying to do log base e of 3 can be a pain. I mean, it's doable, but it can be a little bit challenging to do on the calculator, trying to use e as the base. But log base e actually comes up quite a bit in various applications. It comes up so often that they've actually invented a shorthand for it. And it has its own little button on your calculator even. Let's add this to your notes first, and then we'll actually see how to apply that. Notice log base e of x can be written as ln x. Now when we write ln x, I'm not going to want to read it as now we take the ln of x or something like that. So I would read this as log base e of x. I would read this as natural log of x. Now your calculator actually has a natural log button, and we're going to be making use of that here in a moment. And so back in our problem, rather than writing log base e of 3 then, I can just write that as natural log of 3. So I have 0.03t equals natural log of 3. The natural log of 3 is just a value you can calculate because your calculator actually has an ln button. If you're going and looking for it, it's usually right next to the log button because they're both logarithms. It's just natural log is just a very specific case of logarithm. So go ahead and calculate the natural logarithm of 3. To make sure that you're getting the right number out, you should be getting a number that's about 1.0986. Make sure you can get that before we proceed through the problem. And then once we have that number, we can finish solving this out because I'm going to try to figure out what t is. Right now it's 0.03 times t, so I can take that number that I just found, the entire decimal, so we avoid rounding error, and divide it by 0.03. Now I'm dividing because it was multiplied by t. And so we should be able to get an answer of about 36.62 years if we're taking that to the hundredths place. All right, we're now going to take on a little bit of a focus just on the e and natural log parts. We're going to do 4 last problems here today. So we're going to be doing those 4. So please start by writing down the first of those. take a moment, see how far you can solve it through, and then we'll work it through together. Step 1 will be getting the exponential part by itself. Notice the 2 is not part of the exponential. So the first thing I'm going to do is I'm going to divide both sides by 2. Now before today, we would have then taken this and put it into log form at this point. And that is what we're going to do, although it's going to look slightly different by the time all is said and done. Before, this would have been log, then we put our base. Remember, the base is whatever's raised to the power, so that's going to be e. So it'll be log base e of 400 in this case. And that's what x would equal. Remember, log always equals the exponent. But I'm not going to leave it like this, though. Remember, log base e, it's kind of a pain to calculate. It's a pain to do that, especially when we have something much shorter and simpler. Because the whole log base e, that's just natural log. So if you want to in your work, first write that x equals log base e of 400 and then go to natural logarithm, that's fine. You'll probably find yourself doing that for the first couple days using e and natural logarithms, just while you get used to it. But pretty soon you'll find you can just go straight to the e form or the natural log form. All right, once we have it to this point, x equals the natural log of 400, that's just a value you can calculate. Because that right side, it's just a function and a number. And the natural log of 400 is about 5.99. Next, write down the one next to it, natural log of x equals 5. And go ahead and solve that one out if you can, or at least take it as far as you can. And this one tends to stump us at first. Now, it stumps us because we're not used to seeing natural log x yet. It just isn't habit yet. So a great way to start this is take your natural log of x and first look at it as log base e of x. Because remember, that's all that natural log is. It just means log base e. If I read it like that, you now should be a little bit more comfortable solving it. Because that's more the form that we're used to turning into an exponential. To turn into an exponential. And so in going into exponential form, remember the base of the logarithm becomes the base of the exponential, so that's going to be e. It's to the power of, remember that log always equals the exponent, so that means my exponent must be 5. So e to the 5th equals x. Now, I went ahead and put in this middle step here. And again, that's perfectly fine if you do, but you don't have to. And eventually you get to the point where this goes so smoothly that you'll just go straight to x equals e to the 5th. But that just takes a little bit of practice and just getting used to and comfortable with it. But now notice we have x equals e to the 5th. E to the 5th is just a value you can calculate, which is a little bit weird at this moment because you're still getting used to seeing e as a number. But it is, it's just a number. So do e to the power of 5 on your calculator. You should be getting an answer that's about 148.41. And then once you've done those two, you've seen how to approach these types of problems in general. So go ahead and take on those last two now and see if you can go ahead and get those totally worked out start to finish. All right, for our third problem, e to the 5x equals 500. We already have the exponential part by itself, so I can go ahead and turn it into log form. Now you could start by writing it as log base e of 500 equals the 5x, or you could take that log base e and turn it into natural log straight away. Either way though, I definitely would suggest eventually get it to natural log because that's a lot easier to calculate. Because to do that calculation, we just do natural log of 500. Notice here though, I'm then going to have to divide it by 5. I have to do the natural log of 500 first. I cannot do the 500 divided by 5 because the 500, it is stuck inside of that logarithm. So I can't just divide it by some other number. So once we do the log, then we can divide it by the 5. you should be getting an answer of about 1.24 here. And then for that last one, 7 times the natural log of x equals 2. First thing I want to do is I want to get the log by itself. So that means getting rid of the 7. So I divide both sides by 7. That gives me a big, long, ugly decimal. That's okay. I can just keep track of that decimal. So I now have natural log of x equals that. This now looks just like the one straight above it looked like. So the next thing I'm going to do is write it as an exponential. And remember, if you're having any trouble writing it straight into exponential form like this, it might make your life a little bit easier if you first write it as log base e of x equals the decimal. Just because this is the way you're more used to seeing it. And then you can say, okay, so it's going to be e to the power of that decimal that's going to equal x. And so you did 2 divided by 7. It gave you that decimal. Now all you have to do is do e to the power of that unknown. When you do that calculation, you should be getting an answer about 1.33 if all has gone well.